Welcome to the second presentation in Unit 2 entitled Charged Up. The quote there is opposites attract, which is going to be the fundamental idea behind this unit. It says the learning objectives. Students should be able to identify the factors that affect the attraction and repulsion of charges, and you should be able to determine how charge is conserved in chemical systems. So, chemistry is dependent on the ability to make accurate measurements. Measurements are often converted for analysis, and that chemists are always looking for the relationships between these variables. So those things are what we learned in the first unit. In addition to that, we learned a little bit about the big idea one in the last one, that all matter as we know it is based on substituent atoms or elements from the periodic table. So you should have learned in this lab that charge can be generated by ripping tape off a smooth surface. Like if you just take it right here and you rip it, you generate a charge. And those charges can attract or repel each other when the tapes are brought near each other. And that brings us to our fundamental idea, our big idea number two. The interaction of particles in chemistry can largely be described in terms of Coulombs law and the law of conservation of charge. So that's our big idea number two. But now we need to explore the idea of, okay, what is Coulomb's law and what is the law of conservation of charge? So, Coulomb's law is the relationship between any number of objects that are charged. The charges can be positive or negative. So, if you had a positive charge, it will attract to a negative charge. If you have a positive charge and a positive charge, they will repel from each other. If you have a negative charge and a negative charge, they will repel from each other. That's the origin of the idea of opposites attract. This positive and negative attraction or repulsion. And it's very similar to what people like to look at it in terms of magnets. If you have a north magnet and a south magnet, they will attract, just like if you have a positive and a negative charge, they will attract. This right here is George Augustin de Coulomb, who Coulomb's law is named after. Okay, we have Coulomb's law. It used a torsion balance to verify the well-known fact that opposites attract and like charges repel. He had this really intricate system in which he was able to charge objects and measure the force between the charges. It was a really interesting thing using a torsion balance. Now, using these torsion balances, he was able to modify the distances and the charges to quantify this attraction. Not just say, hey, positive and negative attract, but by how much and what factors changed that attraction, whether it was distance and charge and those sorts of things. So, the greater the distance, the less attraction there was, the more their charges were, the more the attraction was. And so this is Coulomb's law. And you may be looking at this, you are not responsible for this equation right here in chemistry. Okay? It is something that you will explore in physics, but you are not expected to do calculations. In other words, no calculations in chemistry with this. But you are expected to understand the relationship between these. Okay? So we'll just leave it as no calculations. As this goes up, if you increase the charge by going from like +1 to +2, if you increase this number, because you're increasing the number on the top, the force is going to increase as well. Okay, if you increase this charge, okay, let me change color. If you increase this charge right here, the force is going to increase. But if you were to increase, let's say, the distance is the denominator. Whenever you have an increase in the denominator, you're dividing by a larger number, so the force would actually go down. As a result, you need to understand that if you increase the distance between objects, force goes down. If you increase the charge, the force will go up. And this force is the force of attraction or repulsion. This K term is a constant that we won't really talk about much until you get to physics. So, Coulomb's law, like we said, you're not responsible for understanding. You are responsible for understanding the relationship between the variables, but not doing actual math with this. You are expected to understand that increasing the value of charges increases the attraction, increasing the distance decreases the attractions, opposites attract, and likes repel. So, which of the particles below will be attracted? So if you look, whenever we say attracted, we're looking for opposite charges. If you look, this right here is a potassium positive ion. Okay, see this little positive right here? And this is a sulfur negative ion. So because of those things, you have a positive and a negative, and they will actually attract to one another. Okay, this one, there is no charge Because there is no charge, it's not going to be anywhere in Coulomb's law, so we're going to say that it's not attracted. Okay, it says which of the following combinations of particles will have the greatest attraction? So if you were to look at these two, you could say, well, that doesn't make any sense. There's no attraction there at all. So I'm just going to erase it. Okay, if you were to look at these two particles, you would say, okay, well, those right there are going to be the same thing, so there's no attraction, and I'm going to erase that. So now I can look at these two particles, and I can look at these two particles. And what is the difference between these two sets of particles? Well, they're both positive, and they're both negative and negative. The only difference between them is the distance between the charges. And just like when you have magnets, if you hold those magnets close together, it's going to be harder for you to separate them than if you hold those magnets further apart. It's going to be easier to separate them. So the distance term really comes into play. So the one with the greatest attraction or the most force is going to be the first one with the smallest distance. Next, it says which combination of particles will have the greatest repulsion? And you have numbers here. So what combination of numbers is going to give you the most repulsion? So the first thing you can do is you can rule out any of the ones that involve the negative charge. Okay, the negative charge is going to be the one that is going to have, it's going to be an attraction. So you can rule that out and say that particle is irrelevant. So now if you were to look at this, you have a 5 and a 3 that are separated by 9. Okay, then we're going to change colors. And we're going to say there's a 3 and a 4 that are separated by 6. And then finally, you have, let's make the color real different. You're going to have a 5 and a 4 that are separated by this total distance right here, which if you were to look at that total difference, it's 23 micrometers. So which of these is going to give us the greatest attraction? Well, it's not a simple matter of just adding up the numbers, but you've got to look at the formula. Remember, the formula is F equals K Q1 Q2 divided by D squared. And the fact that the distance is squared means that distance is going to have much more of an impact than the charge terms are going to be. So just to put it in the formula, you'd have 5. Let me change colors so I can match. Oh, we'll do this one first. So you're going to take 5 times 4, and then you'd have to divide it by 23 squared, which is going to be a pretty small number. So now we go to red. You'd have 5 times 3 divided by 9 squared. And then for the blue one, you'd have 3 times 4 divided by 8 squared. Okay, so you should be able to rule out one of these pretty quickly. 20 divided by what's going to be greater than 400, it'll probably be closer to 500, we'll say 400, is going to be really, really, really small. Especially when you compare it to 15 over 81 and 12 over 64. Okay, at this point, you could use a calculator if you wanted to, or you could figure out which one's going to be the smallest one. Okay, if we had to pick here, if you had to look at all of them though, and you had to just estimate it, okay, you'd say that this is roughly 1/5. Okay, and if you were to look right here, this is going to be roughly 1/6. So because of that, this one right here is going to give you your 1 divided by 5 is a greater number than 1 divided by 6. So this one right here is going to be our best bet for our greatest repulsion. This is conservation of charge. Certain values are always conserved, meaning that the total value is unchanged. It does not mean that the number cannot change. It means the total of the number cannot change. So as an example, you have 8e. Sometimes 8e is used to show that you have 8 electrons, and another way to say that is to say it's minus 8. Both are considered to be the same thing for 8 electrons. Electrons are negatively charged, so 8e and negative 8 are the same thing. So if you have an object with no charge and you have an object with minus 8 or 8e, when they touch, the charge is actually equally distributed between the two. But then the total still has to remain that negative 8 number. No matter how you do it, the total charge always has to be the same. So charge can be rearranged as long as the total remains the same. And that's what the law of conservation of charge is. Now, when we talk about charge in chemistry, we're talking specifically about the removal or gaining of electrons. So, for example, if I have an object that is neutral, let's say it's 0, and then something happens to it, and now it has a charge of +1, that does not mean that I added a plus charge to it. Okay, that's not what that means. Instead, what it means is that I took away a negative charge. You always deal with negative charges. So if something becomes positive, it's because negative charges were taken away. If something becomes negative, it's because negative charges were added to it. We only deal with negative charges, which are electrons, which we'll deal with a little bit more in Unit 4. Okay, it says if the total charge in the universe is 0, then how can I have an object with a charge of +2? And the answer is if you have a neutral object, you have to have another neutral object that when this becomes +2, the other one becomes -2. What it means is it says for the entire object or the entire universe, the total charge or the sum of all the charges is equal to the same number. It doesn't mean that it can't affect individual charges. Okay, individual things can take charge, lose charge, but the total charge in the universe has to be the same. So when lightning leaves a cloud and it transfers its charge to the ground, so now all the charge is here, what that means is that the charge is no longer here in the cloud. So you've transferred the charge, but the total charge is the same. Next, it says in a battery, the Zn is turning into Zn2 plus. What is the tin doing? So in this case, you have Zn2 plus. Okay, so if you have Zn going to Zn2 plus, okay, you are becoming positive. Okay, which means that you have some sort of those negative charges have to go somewhere, and that's the same thing that we have. We have the Zn2 plus are going to Sn. The tin is doing this because as this thing becomes positive, this thing has to lose positive charge or gain negative charge. Now, if this is a little bit confusing to you, this is something that we will not really see until Unit 10 again. 100 grams of aluminum is converted into Al3 plus. How many moles of electrons are separated? So the first thing is if you have aluminum, aluminum is this. It's going to go into aluminum 3 plus, which means that I have to take away 3 electrons from each aluminum in order to do that. Okay, that's the only way to make these charges balanced because you can't those charges have to go somewhere because of the law of conservation of charge. So, if I have 100 grams of aluminum to begin with, and I take that and I divide it by the 27 grams of aluminum, I get 1 mole of aluminum. Every 1 mole of aluminum, you lose 3 moles of electrons. Okay, at that point, you could stop the calculation if that's what it was asking for. So if it wants you to answer in terms of moles of electrons, that would work. Um, but if it doesn't, then you could go from there and you could say 1 mole of electrons, and you should know that 1 mole of electrons is 6.022 times 10 to the 23rd from Unit 1. At this point, you would multiply and divide, and you would get your answer for the number of electrons that you would separate out.